Hi there, my name is Heath. This is the first of two video lectures on section 8.5, which is probability. A random variable is a variable that returns a real number, but the value is not predetermined because the value is based on the outcome of an experiment. We say that x is a random variable in this case. Here's an example. An educational researcher visits a randomly selected classroom and counts the percentage of female students. That percentage is a random variable. We don't know what the value is until we actually go into the classroom and count the percentage of female students. Here's a different example. An industrial engineer randomly selects a light bulb from a box. The engineer measures the lifespan of the light bulb under continuous operation. That lifespan is also a random variable. Every random variable has associated with it a probability density function. It's a function that satisfies this property. If a and b are any real numbers with a less than or equal to b, then the probability that x is between a and b is given by the integral of the function f of x. In other words, if we look at the function from a to b, the area underneath that function is the probability that x is between a and b. So it's a function that gives us probabilities in the form of integrals. In order for that to work, it means that the probability density function always has to be greater than or equal to 0 because the probability can't be negative. It also means that the total integral under the function has to equal 1 to represent 100%. So let's do an example. Let's look at this function here. We want to show that this function is a probability density function. So the two things that we need to check are, is this function positive? And the answer, yes, it is a positive function. Does the area equal 1? We don't need calculus to answer this question. If I think of this as a triangle, the base of the triangle is 10, and the height of the triangle is 0.2. And the area is 1/2 times the base times the height, which is 1/2 times 10 times 0.2, and that's equal to 1. And so this is a probability density function. Any questions? I hope not, because I can't hear you. So let's look at an example using this probability density function. What is the probability that a random variable is greater than 7? Here's 7. We want to find the area under the function that is beyond x equals 7. That's the integral from 7 up to 10 of f of x. And it's easy to eyeball this. Again, this is a triangle. The base of the triangle is 3, and the height is 0.1. Area is 1/2 the base times height, which is 1/2 times 3 times 0.1, and that's equal to 0.15, which is 15%. Use the same probability density function to find the probability that x is between 2 and 7. So we want to find the area here. And I would do this in two parts. The area down here is a rectangle. The base goes from 2 to 7, so the base is 5. and the height is 0.1. And so the area of the rectangle. And then let's look at the triangle above it. The area is also, the area is 1/2 base times height. The base is also 5, and the height is 0.1. And so the area is 0.25. And if we combine these, the total area is 0.75, which means there's a 75% probability that x is between 2 and 7. So this isn't a hard example, I'm hoping. This is an example that we can solve just by using basic geometry. Let's look at a harder example. Let's show that this function is a probability density function. So it's not too hard to check that a function is greater than or equal to 0. We can check that because we know that e to the x is always positive, so the numerator will always be positive. And the denominator, because it's squared, the denominator will always be positive. And positive divided by positive is always positive. But we also need to check that the area under this integral is equal to 1. We only have to integrate starting at 0 because my domain is x is greater than or equal to 0. Okay? So if we work out this integral, there's a lot of steps here. Hold on. We want to integrate from 0 to infinity. We replace the improper integral with a limit as t goes to infinity of an integral from 0 to t. And then we use a u substitution to simplify this integrand. We'll let u equal 1 plus e to the x, and then du is equal to e to the x dx. When we make that substitution, we get 2 du over u squared. And then my bounds change from 0 to 1 plus e to the 0, which is 2, and from t to 1 plus e to the t. The integral of 2 over u squared is negative 2 over u. We'll evaluate that over our bounds, and we get negative 2 over 1 plus e to the t minus negative 2 over 2. As t goes to infinity, this term goes to 0, and this term goes to negative 1, but we're subtracting the negative 1, so my final answer is equal to 1. The integral is equal to 1, and therefore we have a probability density function. So let's say this is a probability density function for a random variable that's measured in hours. How would we find the outcome? That the probability that the outcome will fall somewhere between 2 and 5 hours. We would need to integrate from 2 to 5. And we already know what the antiderivative of this function is because we did that a moment ago. It's the integral of 2 over u squared du as my boundaries go from 1 plus e to the 4th to, 1 plus e squared to 1 plus e to the 5th. And that's negative 2 over u evaluated at 1 plus e squared and 1 plus e to the 5th. And at this point, this becomes a calculator problem, and the answer turns out to be approximately 22.5%. Same function. What would be the probability that the outcome is greater than 1 hour? So we have to solve. We know we're going from 1 hour, but we don't have an upper bound. And since this is an improper integral, we'll take the limit as t goes to infinity of the integral from 1 to t of f of x. And again, that's positive 2 over u squared, going from 1 plus e to 1 plus e to the t as t goes to infinity. And that's the limit as t goes to infinity of -2, this is where the negative comes in, over u, evaluated at 1 plus e to the t and at 1 plus e. And again, this is a computational problem, but the answer turns out to be about 53%. In the next part, we're going to look at the mean and the median of a probability distribution function. What's the average value that we could expect for this random variable, and what's the median value we can expect? I hope you enjoyed this. Good luck.